Good morning in Asia and Egypt. Good evening in the United States. Ladies and gentlemen, welcome to the second International Conference on Advanced Technology and Multidiscipline, Icatam 2022. With the theme of supporting sustainable development goals through innovation on advanced technology and multidisciplinary research, October 12 and 13, 2022.
I'm Atala Raffi from Nanotechnology Engineering, and my partner.
I am Ola Claudia Estepu from Electrical Engineering.
We will be the master of ceremony for the first day of Icatam 2022.
Icatam is an annual international conference organized by Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga, Indonesia.
This conference aims to explore global knowledge on science, information, and advanced technology. Icatam provides a place for researchers, engineers, and scientists around the world to build a research connection and collaboration, as well as sharing knowledge on how to address worldwide problems through discovery of cutting-edge science and technology. The conference covers the latest research, knowledge, and innovation in the field of electrical engineering, nanotechnology engineering, industrial engineering, data science technology, and robotics and artificial intelligence.
We would like to give to our deepest gratitude for your esteemed presence today. His Excellency, Vice Rector, Sub Research, Innovation, and Community Development, Universitas Airlangga, Dean of the Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga, along with all the deans in the Universitas Airlangga and the chairman of Icatam 2022.
It is an honor for us to introduce and welcome the keynote speaker for this conference, Dr. Gunawan Prihandana from Universitas Airlangga, Indonesia, Professor Kim Lim from Kumo National Institute of Technology, South Korea, Professor Tomoteru Fukumura from Tohoku University, Japan, Professor Darren Lipomi from University of California, San Diego, United States, Professor Dr. Kaharudin Dimyati from University of Malaya, Malaysia, Professor Tarek Mohammed from Beni Suef University, Egypt, and all honorable invited speakers who attend today's conference.
This conference will begin with singing our national anthem, Indonesia Raya, and hymn Airlangga, and continue by
welcome remarks by Vice Rector Sub Research, Innovations, and Community Development of Universitas Airlangga, the Dean of FTMM, the Chairman of Icatam 2022.
The first plenary session will be given by Dr. Gunawan Setiawan Prihandana from Universitas Airlangga, Indonesia.
After that, we'll see an incredible video presentation by PT Lab Sistematika Indonesia as our partner. The second plenary session will be given by Professor Kim Lim from Kumo National Institute of Technology, South Korea.
The third plenary session will be given by Professor Tomoteru Fukumura from Tohoku University, Japan.
After the plenary sessions, the parallel sessions will begin. Before we proceed further, we would like to invite you to solemnly hear the Indonesian National Anthem, Indonesia Raya, and Hymne Airlangga.
Indonesia
ladies and gentlemen, we will listen to the speech by the chairman of Icatam 2022. Please welcome Dr. Tata Amrila. Dr. Tata Amrila, the stage is yours.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning from Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga, Indonesia. Dear Director of Universitas Airlangga and or the representative, Dean of Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga, distinguished guests, speakers, participants, ladies and gentlemen. Welcome to our international conference. It is a great honor for me to be addressing you today at this second international conference on advanced technology and multidiscipline 2022. I also would like to give a high appreciation to the many individuals for the contribution and support on this international conference. It is important to note that the first conference was held successfully on 2021 with a lot of experts from around the world sharing newest findings in their field. Here, today, the second conference is held again, and we hope that this event is continuing to success of the previous conference, as well as giving a new breakthrough in the advanced technology through multidisciplinary research. As mentioned previously, this conference aims to explore global knowledge on science, information, and advanced technology. This year, our theme is supporting sustainable development goals through innovation on advanced technology and multidisciplinary research. This theme support UN SDGs agenda. The conference covers the latest research, knowledge, and innovation in the field of electrical engineering, nanotechnology engineering, industrial engineering, data science technology, as well as robotic and artificial intelligence. With the topic and research area are intelligent power and control engineering, renewable and sustainable energy technology, digital health, data-driven decision support system, human factor and system engineering, advanced manufacturing and computational approach, nanotechnology and nanomedicine, and environment and food technology. From those topics on multidisciplinary research, here we invite 6 keynote speakers and 11 invited speakers, as well as more than 50 participants from around the world join to this conference. Ladies and gentlemen, I'm sure that you will have fruitful and rewarding exchange through this event. I wish you every success with this important conference, and I look forward to learning about the outcome. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Dr. Tata Amrila, for the opening remarks. Next, we are going to listen to the welcoming speech from the Dean of Faculty Advanced Technology and Multidiscipline, Universitas Airlangga. Ladies and gentlemen, please welcome Professor Dr. Dwi Setiawan.
Assalamualaikum warahmatullahi wabarakatuh. Good morning from Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga, Indonesia. The distinguished guests, speaker, participant, ladies and gentlemen, welcome to our international conference. It is a great honor for me to be addressing you today at this second international conference on advanced technology and multidiscipline, Icatam 2022. I would like to take this opportunity to thank the host of this international conference, the Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga. I would also like to echo the chair appreciation to the many individuals who have worked on this international conference. This event would have been impossible without the support each and everyone present here. Moreover, I honorably welcome our keynote speaker and invited speakers. The honorably keynote speaker for today are Professor Kim Lim from Kumoh National Institute of Technology, South Korea. Professor Tomoteru Fukumura from Tohoku University, Japan. Professor Darren Lipomi from University of California, San Diego, United States. Professor Dr. Kaharudin Dimyati from University of Malaya, Malaysia. Professor Dr. Tariq Mohammed from Beni Suaif University, Egypt. Dr. Andrea Fiorani from Keio University, Japan. Dr. Firman Mangansa Simanjuta from University of Southampton, UK. Ilma Mufidah, PhD from Telkom University, Indonesia. Ahmad Ataka Awalurizki, PhD from Universitas Gajah Mada, Indonesia. Muhammad Abdillah, PhD from Universitas Pertamina, Indonesia. And Satria Loka, PhD from Ghent University, Belgium. And speaker from Faculty of Advanced Technology and Multidiscipline, Universitas Airlangga. It's good to be here and have the opportunity to talk about global knowledge on science, information, and advanced technology. Icatam 2022 aims to provide you a place for building research connection and international collaboration. Today, conference themes is supporting sustainable development goal through innovation of advanced technology and multidisciplinary research. It is high time that such an event took place to highlight the remarkable contribution which advanced technologies and multidisciplinary perspective make in so many areas of our life. A glance through the list of presentation plans today and the next day reveals the amazing diversity of advanced technology application. Conference such as this provide a valuable opportunity for research scientists, industry specialists, and decision makers to share their experience. I am grateful to the many experts who have come to share their knowledge today and the next day. I also welcome the many representatives of government, industry association, and general participation who have joined us. I am sure you will have fruitful and rewarding exchanges through this event. I wish you every success with this important conference, and I look forward to learning about the outcome. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Dwi Setiawan, for the welcoming speech.
Ladies and gentlemen, we kindly remind you to please turn on your camera.
We will listen to the speech by Vice Rector Sub Research Innovation and Community Development of Universitas Airlangga. Please welcome Professor Dr. Ninyoman Tri Puspaningsih. Professor Nyoman, the place is yours.
Yeah. Thank you for the MC. Assalamualaikum warahmatullahi wabarakatuh. A very good morning from Universitas Airlangga, Surabaya, Indonesia. The honorable keynote speakers, Professor Kim Lim from Kumoh National Institute of Technology, Republic of Korea, Professor Tomoteru Fukumura from Tohoku University, Japan,
Continuing.
Professor Darren Lipomi from University of California, San Diego, United States of America. Professor Dr. Kaharudin Dimyati from University of Malaya, Malaysia. Professor Dr. Tarek Muhammad from SUF University, Egypt. Gunawan Setia Prihandana, PhD from Universitas Erlangga, and also the honorable invited speakers from Universitas Erlangga, Universitas Pertamina, Telkom University, Universitas Gajah Mada, Keio University, Japan, Ghent University, Belgium, and University of Southampton, United Kingdom, that I cannot also mention one by one. The Honorable Dean of the Faculty of Advanced Technology and Multidiscipline of Universitas Erlangga, Professor Dr. Dwi Setiawan, the Chairman of International Conference on Advanced Technology and Multidiscipline of 2022, Dr. Tahta Amrila, the Director, Vice Dean, Academic Community of Universitas Erlangga, panelists, moderator, participants, and representatives from partner university, academia, all the distinguished guests. Ladies and gentlemen, Alhamdulillah, praise be to Allah, the Almighty, for giving us the opportunity to gather here today. On behalf of the Rector of Universitas Erlangga, Professor Muhammad Nasi, it is my utmost pleasure and honor to welcome all of you to the second International Conference on Advanced Technology and Multidiscipline, or Icatam, of 2022. Under the Faculty of Advanced Technology and Multidiscipline of Universitas Erlangga, today's conference will address the issue related to the supporting sustainable development goals through innovation on advanced technology and multidisciplinary research. This international conference aims to explore the global knowledge on sciences and also information and advanced technology, and serve as an international forum for researchers, engineers, and scientists around the world to build research connection and collaboration. Distinguished participants, the 2030 Agenda from United Nations, which is also referred to as SDGs, is universal and transformative, and aims to promote common prosperity, advance social progress, and protect the environment while leaving no one behind. Universities must be able to be the pioneer in overcoming this problem scientifically, including but not limited to support the SDGs of United Nations. As a higher education institution, we need to boost cooperation within interdisciplinary research that can enhance the productivity and sustainability that can benefit society. We are constantly evolving to make remarkable advances by integrating applied and fundamental science for productive and efficient scientific research, and such collaboration is crucial. The Icatam has drawn in forthcoming researchers, experts, and practitioners together and looking for future cooperative work among institutions which will lift the visibility of scientists or academicians in building an academic network, and an opportunity to boost the cooperation both national and international. The conference covered the latest research on knowledge and innovation in the field of electrical engineering, nanotechnology, industrial engineering, data science technology, and also robotic and artificial intelligence. I believe during this scientific conference, it will provide a vibrant platform for all of the participants to share ideas, explore the potential of new advances in technology, and foster closer ties. No doubt you will have your hands full during this conference. While concluding, let us acknowledge the outstanding effort of the Icatam of 2022 to organizing committee for the great effort in ensuring that the international conference is conducted smoothly and successfully. Congratulations for the whole organizing committee and also the Faculty of Advanced Technology and Multidiscipline. And also to all participants, thank you for being here, participating, and also lending your expertise on this crucial topic. The active participation and cooperation of the participants who have gathered here today will be very meaningful, not only for Indonesia, but as well as for the global society. Once again, welcome to Icatam of 2022. Together, let us accelerate the exchange of ideas and scaling up of good practices. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Professor Nino Mantri Kusmaningsih, for the opening remarks. Ladies and gentlemen, we would like to express our gratitude to PT Lab Sistematika Indonesia for being our sponsor and supporting Icatam 2022.
Before we proceed into the next session, please rename your Zoom name to be name underscore institution.
Ladies and gentlemen, we are delighted to begin the plenary sessions that will be delivered by Dr. Gunawan Setia Prihandana from Universitas Airlangga and moderated by Ms. Astari Rahmania, MSc. Time and place are yours.
Good morning, everyone. I'm so honored to be here today in International Conference of Advanced Technology and Multidiscipline 2022. My name is Rizky Astari, and I'll be your moderator for this session. Our first keynote speaker today is Dr. Gunawan Setia Prihandana, who is currently an assistant professor here in Industrial Engineering program, Universitas Airlangga. Dr. Prihandana graduated from Universitas Gadjah Mada, in which he got his bachelor's degree in mechanical engineering. He then continued his study at University of Malaya, where he got his master and PhD in engineering, design, and manufacture. Our topic for this session is flat sheet polymeric membrane, a simple fabrication and its application. Now, without further ado, I'm delighted to welcome Dr. Prihandana. Please, the stage is yours.
Like to share my work about the simple fabrication and modification of polymer sheet membrane. So, and also application in the water filtration process. So let me proceed next. Okay. So the background of research is coming from when we are collecting the water from all over the city in Indonesia. So we have like a different type of water. For example, you can see here we have like water sample type A, type B, and type C. So this water is coming from some area in Indonesia. The problem with water A is like it has like a yellowish color, and the water type B has like yellowish color but with some color in the water. And for the water type C, it's very clear, like just like normal water. So probably people will think that the water C is the safest, it's easy, it's safer to drink. And then we tried to do some small tests on this sample, and then also we sent this sample to another lab, and then we got a very interesting result. So people will think that water sample C is maybe the safest one because it's clear, it's like a normal water. But unfortunately, that the water sample is the safe to drink. But water B and water C is not safe to drink because of the color. So sometimes we are confused which type of water that can be used or can be drink. That's why in here we try to make some modification of the membrane. Also, we try to do some like research how to treat the how to treat the water, and so people will have no problem in consuming the water. So people now they have many type of filtration method. The first one is like a traditional water filtration method. So normally people will just do some like a boiling. They just boil the water and then they will get the boiled water will like kill the microorganisms in the water. The problem with this is like we need to more fuel and also we need the cooking equipment. And also, when we have some particle or some chemical, also some heavy metal in the water, it's going to be difficult for us to remove this from the water. That's why some other people, they try to use like a chemical method. This chemical method is much easier because what you need only just like a chlorine tablet and just put in the water and just leave it for hours, and then you will have safe water to drink. The problem with the chlorine water is that when you don't properly put enough small amount of the chlorine, you're going to be like damage your health at long-term use. That's why some people now try to use like better methods by using like a membrane or surrounding method. Okay. In order to overcome the problem coming from the boiling water, also coming from the chemical for the water purification, some researchers they're developing like a membrane filtration and then so ceramic filtration. For the ceramic filter, it's much easier compared to like membrane because it's much inexpensive, it's cheap, and also it can be used to remove the bacteria in the water. And the flow rate is quite high because just using the gravity. So I mean, you don't need electricity to run the process of the filtration. But the problem is that it's only effective against the bacteria. When you have virus in the water, and when you have chemical contaminant in the water, it cannot be used directly. So that's why we need to do some like a combination between what kind of filter that can be used to remove the water, because water is different from in any area. So in order to do that, we developing a membrane that can be used to clean the water. So membrane basically they're using two type of mechanism, diffusion mechanism. The first one is molecular sieving. In molecular sieving, membrane have very small pores, and then this small pores will reject the bigger molecule. So it's only allowing some smaller molecule than the membrane pores to come into the membrane. The second diffusion mechanism is by using solution diffusion. So the molecule will diffuse in the membrane, and then allowing solution to pass through the membrane pores. So when we have this membrane, so what's kind of parameter that we consider that membrane is good or membrane is bad? So in the membrane world, people will have like permeability and also selectivity. So when we can say that membrane is good when we have the membrane with high permeability, also high selectivity of the membrane. And then actually membrane is not only can be used for the water treatment process, membrane also can be used for like gas purification. For example, some medical researchers they are developing the membrane for medical mask, and then they also use the membrane for separating the nitrogen and oxygen in the air. Also, some researchers they use the membrane to capture the carbon, and then they use the carbon for other applications like for extinguishing. So maybe we all know that membrane also can be used and mostly used for the water treatment process. So because by polymeric membrane, we can control the porosity of the membrane. You can control what type of membrane that you want to have. So membrane they have, the polymer they have like a type of membrane. The first one is microfiltration, and the ultrafiltration, nanofiltration, and reverse osmosis membrane. So if we want to remove the bacteria, so we just use the microfiltration. If you want to use the virus, you can use the ultrafiltration membrane. Okay, so membrane, they will remove the pollutant in the water by controlling the porosity of the membrane. So we can modify them, so we can do as we like, because it's much easier also to fabricate the next. I will try to explain how we can make a membrane. And then another researcher, they also use the membrane for medical purpose. So they are making the membrane for blood purification. When they do what they use like a semi-permeable membrane. It's mean like they will do like a dialysis solution and also the blood solution. So they will like exchanging ion between ion in the blood and also pollutant in the blood and ion in the dialysis solution. And then they will have like a clean blood, then we go back to the patient body. And some researchers also they are using what we call microfilter membrane because they can control the membrane porosity. They can make the membrane permeable, so they don't need dialysis fluid. And also, they don't need pump to circulate the membrane. And then maybe we all still remember that we had problem with the COVID like 2 or 3 years ago. We have a COVID pandemic all over the world, right? So some people they try to developing the membrane for mass medical purpose. So yes, so membrane also can be used for the mass medical purpose. We can control what kind of bacteria, what kind of virus that can be filtered from the membrane. So this is one of the applications of the membrane. And then one of the problem in membrane making is probably the membrane fabrication, but actually this one is not so difficult. There are many types of that can be used to make the membrane. One is the easiest way is by using the phase conversion method. Phase conversion method means like there is a changing phase from the liquid to solid. So when we have what we have to do in this process, we need to prepare the drug solution. So we call it the drug solution for the membrane solution. So we have like a polymer dissolved in the solvent, like organic solvent. And then once we have the solution, we just pour the solution into the glass slide of glass slide, and then we just spread out the polymer solution into the glass slide. Once we have the uniform thickness of the membrane solution on the glass slide, we just immerse this glass slide into the coagulation bath. Coagulation bath is filled with the pure water. So during the coagulation process, they will be like exchanging from solvent to non-solvent coming from the water. And just leave it for like few hours, then we will have like a nice flat sheet polymeric membrane here. And then membranes, sometimes membrane is not perfect. Sometimes we need to do some modification. Sometimes we need to put something inside the membrane, and we can improve the performance of the membrane. So like maybe like 10 years ago, we are having a problem with the membrane falling. Membrane falling means like when we use the membrane for the sterilization process, sometimes the pollen, such as bacteria, like particle, they will stick into the membrane surface. When this one deposited a lot in the membrane surface, it will just like block the membrane force, and then finally it will like reduce the permeability of the membrane. In order to do this, we did some modification by using like a polydency coating, and then also by using the diamond-like carbon coating. This one works perfectly in improving the membrane performance. As you can see here, there's like some like a pollutant or some like blood stay in the superficial membrane without having like modification. But when we have the modified surface by using like a polyethylene or the FDLC, we have now like no spots on the superficial membrane here. So this system is good, this method is good, but the only problem is it needs like a high tech equipment, and also very expensive. Not every lab they have this kind of polyethylene coating machine. Not every lab they have the FDLC coating machine. Also need a lot of money to make this modification. Therefore, we try to do some simple modification. First, we just added some additive. Additive can be anything. Just like for this case, we use the nanoparticle silver. We just put into the dop solution of the membrane, and then we just make the membrane just like the pressing method, and then we will have nice flat sheet membrane with the particle inside the membrane. silver is good for bacteria because they can like modify the metabolism of bacteria, and then bacteria will not be able to duplicate and then go into the dead space for the bacteria. And then once we have the membrane, plastic membrane, we need to do some tests. So normal tests we can done here. It's very simple test. First, we need to do the water contact angle test, and then we need to do the permeation test and the antimicrobial test. So for the water contact angle test, we just drop water liquid into the membrane surface, and then we just check the contact angle of the membrane. For the permeation test, we need to have this kind of setup. First, we need to have the liquid nitrogen gas. And then nitrogen will push the water inside the dead end shell. And there is a membrane here. And the membrane will like prevent the dirty from the water. So normally we use the pure water for the pure water flow test. And then by measuring the concentration on the volume of the permeate here, then we can see the difference of the membrane. Is it membrane good or is it membrane bad membrane? So for the microfiltration membrane will only be able to reject bacteria, but for the ultrafiltration membrane can be used for the virus as well. And then for the antimicrobial activity, we just use like a microbiology test for the membrane that's test on the surface of the membrane. So for the antimicrobacterial test, we use the same setup, but we need to change the pure water to like contaminated water, like river water, irrigation water that has so many bacteria inside the water. And for the water contact angle test, we got the result nicely actually. So by having 0.1 weight percent of the silver nanoparticle, we can have the hydrophilicity of the membrane. So this is good. I mean, when we have this very low contact angle, meaning like the water will just pass through the membrane without staying on the surface of the membrane. And then for the pure water flux test, the 0.1% of silver nanoparticle increase the pure water flux means that we can have higher flow rate compared to the membrane without the silver nanoparticle, a bit more percentage of nanoparticle. And for the antimicrobial activity, we can see here with the increase of the concentration of the nanosilver particle, there will be like a decrease in the bacteria colony growth on the membrane surface. So I mean that the silver nanoparticle work perfectly well in controlling the growth of the bacteria colony. And another simple modification on the membrane is by using whatever available in Indonesia, for example. So in Indonesia, we have like a non-woven fabric. It's commercially available in Indonesia. So we have this company in Surabaya. So it's not open like some material that used for the mask, for the medical mask. But the only problem with this non-woven is they have like a big space between the fiber and the non-woven here, like just like you can see here. So this space will allow some bacteria, also some virus goes to the membrane pores. So the only way we try to close this space is by adding some like a coating. So we control the polymer type polymer, we control the solvent, we control the concentration, and then we do some special coating technique. And then we have the thin film on the membrane surface. You can see it. So the thin film will improve the rejection of the bacteria and also the virus. So can I play the movie? I want to play this movie. Cannot play the movie. Yeah. Okay. Okay. Then we actually for this membrane, we don't have the facility here. That's the problem. This is the challenging thing in Indonesia. We could make something good, but we don't know where we want to test. So we need to send this sample to Japan. So we sent the sample to Japan, and they did some experiment, they did some tests for the sample. So actually the results coming quite good for this. We have like BFA bacterial efficiency like 91.5%, and for the viral efficiency like 83.4%. But this is just like a preliminary experiment. We still can improve the performance of this membrane actually by changing, also by modifying the technique. And so membrane is not only just like fat seals or not just like coating thing. So we can also use the membrane as a glue. So people now they are using like activated carbon powder for the filtration system in their economy, their hospital. But the problem is that the powder is there's still space between the powder. So some company they try to make the what they call carbon block. Carbon block is like the compacted one of the activated carbon powder. So they have this carbon block like this. So the only problem is this one is very difficult to make the carbon blocks. It's very expensive. You need like a high temperature furnace. You need like a high compacting pressure engine to compact this carbon block. It's very costly for electrification. So what we tried to do here is we use the membrane solution as a glue. So membrane will put the powder together and then we just compress into like a shape, like a cylinder shape. Or maybe we want to change like concept. It depends on the mold that we have. So in this cone or in this dish, the membrane will have two different jobs. The first job is they put the powder together. The second job is they act like a permeation membrane. So they filter out the bacteria, the dirt in the water. So when we don't have the membrane between the activated carbon particle, you can see it. There's some like bacteria, some virus, they will go through the space between the activated carbon powder here. So it means like the efficiency of the production will become very low. But when we have the membrane between the powder like this, the membrane will do like a filtration also for the bacteria, for the virus, and so for the particle in the water. So we did some filtration tests. So actually this one based on the gravity force, just like the ceramic membrane. So we just put the water in the container and then we just leave it for like a few minutes and then we have the pavement water here. And then we test the pavement water based on the filtration and also the total quality from here. So we had like, we use like a 30% of PS solution, weight percent of the carbon active carbon and also 50% weight percent of the PS solution here. And so we get the water sample from irrigation river in Yogyakarta, Kaliduran River. So and then we have this kind of result. So basically, by using the activated carbon, we can reject like bacteria in the virus, like bacteria in the water, like 99.9%. But when we only use the carbon powder, we can only reject like 90% of bacteria in the water. We did also some tests by using iron, like a heavy metal waste, like iron in the water. So we have like a water sample like with 10 ppm of iron in the water, and then we use like a test packet from Kyoritsu to check the water the concentration of the iron in the water. So we can see here when we use the powder, we can only remove like a half of the iron in the water, but when we use activated carbon, we can remove almost all the FAR in the water. So we have the flat sheet membrane, we have the membrane for the glue, we have the membrane for medical mask. So what are we going to do next? Just flat sheet membrane is not enough for the water filtration process. We need to do something more. So this is why the people try to utilize the membrane in order for the water filtration system. So there are two types of most people they use two types of this membrane model. We call it membrane model. So we have like a flat and frame module and the spiral wall model. For the flat frame model, it's more like a photo frame. So photo frame with the membrane on the back and on the front of the frame. So the fluid is coming like a gas, also water is coming here, and then they will push through the membrane here, and then we coming out as permeate here. So then we can collect the clean air, clean water here. The only problem with this model is that it's very limited space, limited area of permeation area. So that's we don't really use it. And also we need to care about the leakage coming from the tank here. So people normally they don't really use this one. For the second one, we use the spiral one model. It's much better compared to the flat frame model. This spiral one model, we just like roll the membrane. It's coming from like a 2 sheets of 1 meter length of membrane and with 30 centimeter of membrane width, and then we can roll it, and then we have like a spiral module here. So the dirty water is coming here, and then due to the pressure between the membrane, and then we have the clean water inside the tube. So we have the spiral module. So what are we going to do next to get this work into the filtration system? Okay. Can I play the movie here? I need to play the movie. Cannot. Okay, okay. So this one is the movie. Yeah, it's a movie that we are doing some small experiment. So we have a humic acid solution here, and then humic acid solution, and then we use the spiral model here on the back, and then we try to draw that by using pump, and then the water is coming here, then we like the clean water here. This is that, but we cannot play the music. Okay, and then next we have oh, sorry, this one. Okay, yeah, we can play the movie. Okay. So this is the module, this is the humic acid solution, and then this is the module. And then you can see here that humic acid is going into the module, housing module here. And then the spiral one module will do the job to clean the humic acid water, and then we will have like clean water here in the second bottle here. So the water is coming out from the module is very clean. So yes, you can say that the module, the membrane is successfully clean the water in the humic acid. Okay, okay, we have this system, small system, but we need to install the system into bigger system. So we have like a small experiment with the Panasonic guy. Panasonic is one of the biggest appliances company in Indonesia and in Japan. So we have small collaboration with them. So they have this kind of water dispenser, Panasonic one. So this water dispenser is they use normally they just like use the small water tank here, and then there's the pump, and the pump will like draw the water from the pump will draw from the tank here. But Panasonic have an idea. They want to use the filter inside this water dispenser. They already got the filter from US, but the problem is quite expensive, and maybe it's more expensive than the partial water dispenser. Then they contacted us, and then we find a solution. So we installed our filter into the water dispenser, Panasonic water tank here. So first, we need to draw the water from the water source here, and then we just store it in the water tank here, and then the water tank will go into the WPS, it's from Panasonic, and then from the WPS it will go to the water dispenser, and then from here we will get water that's safe to drink here. Yes, I think that will be all for my presentation today. Thank you very much.
Thank you, Dr. Prihandana, for the interesting presentation, which I'm sure the audience have a lot of questions about. But before we get to the Q&A session, please, for the participants to fill in the attendance form. The link is on the chat box. Thank you. Now, for this session, we're doing one question at a time. So if you have any question, you could raise your hand or type your question in the chat box. It seems like we have already one question from Ilma. Thank you for the question. The question is, what kind of bacteria can be filtered using this membrane? Please,
Okay.
I'll let Dr. Prihandana to answer the question, please.
Thank you for the question. So actually, any kind of bacteria, because the membrane, they do the filtration based. So it's, the good thing about microbial membrane is good. It has high permeability compared to ultra or nanofiltration membrane. But the only problem is like maybe it's not as the filtration membrane is not as good as the filtration because it only can be used for the bacteria only and also some colloid. But also, of course, we need to control again the porosity on the membrane because some I don't know, maybe some bacteria is smaller than because some bacteria they have many different sizes, but principally as long as the porosity of the membrane is smaller than the bacteria, it can be used to filter the bacteria, any bacteria. Gram positive, gram or gram negative also can positive bacteria can be filtered by the membrane.
Okay, thank you, Dr. Prihandana, for answering the question. We have another question from Intan. Is it possible to apply the green synthesis, for example, using plant extract, microorganisms, biomass, and etc.? I'll let Dr. Prihandana answer this question, please.
Okay, thank you for the question. It's very interesting question. So for the making the membrane solution, we need polymer and also organic solvent. When we have this silver nanoparticle, when we can dry this nanoparticle, like maybe when we can dry all the particle, so we can just add into the DOP solution. But when we have when there is like a water in the silver nanoparticle, we just like coagulate the membrane solution. So maybe the other idea is by using like spraying method. So when we have the membrane, we just dip the membrane into the silver nanoparticle solution, and then we will have like a membrane attached. Silver membrane attached to the membrane solution. But yes, but it's possible. Maybe we can, but also maybe we can try like a different type of solvent. For example, some polymer they're properly dissolved in the water, so like a PEEK, they dissolve the water. But for the polymer that can only be dissolved into the organic solvent, it's maybe difficult when we have water into the when we have the water in it. So maybe we have to choose carefully with what kind of type of the solvent that used for making the silver nanoparticle. Is it water or is it organic solvent? Thank you.
Thank you, Dr. Prihandana. We have another question from Javan. Please excuse my pronunciation. The question is, how is the reusability of the polymeric membrane? And is it possible to make reusable polymeric membranes from waste, such as plastics?
Okay, thank you.
Dr. Prihandana answer this question.
Okay, thank you for the question. So maybe already explained by the moderator this kid that my background is mechanical engineering, so I'm not a chemist, not a chemical engineer. So I just try to explain membrane based on my view as mechanical engineer. So yes, it's possible to use the polymer membrane. Yes, we can use the polymer membrane. So but basically when we already use the polymer, they will like some pollen deposit the membrane. So we have to wash. We can use like a backwash to clean the membrane. So is it possible to make reusable polymer by using some spot? Okay. So membrane, as long as it's polymer, as long as it can be dissolved in solvent, yeah, we can use them as we can use them to make a membrane. For example, some researchers they dissolve the PET bottle, PET plastic, and then but they use I don't know some special solvent. Maybe the can understand about me. There's some different solvent they try to dissolve this plastic, and then when they have like a membrane solution, then they just use the same like impression method to make membrane. Yes, I think it's possible to make a membrane come from like a PET bottle. That's very interesting also when we can make this one.
Do we have any more questions from the participants? While we wait, then I'll be the one asking questions then. We know that the water in Indonesia is not doesn't have the best quality of water. So I'm interested to know what type of membrane or filter is suitable for water in Indonesia.
Well, that's a difficult question. Difficult question. Difficult to answer the question. Okay, I'll try my best to answer the question. So, water is different from every area in Indonesia. We understand that some water they have like hot water, they have water with bacteria, with virus. As I said previously, we need to do some like a combination filter to clean the water. So we cannot only depend on the membrane. We cannot only depend on the ceramic membrane. We can only depend on the activated carbon and absorbent. So this type of filter they have good and bad. For example, if we want to clean the water in Surabaya, for example, like a salty water in Surabaya, it's difficult to use the ultrafiltration membrane. It won't work. So we need to use like RO membrane. The only problem with RO membrane is very expensive. The system is expensive. We need like a high pressure pump with high pressure, and the water flow is very slow, very low, maybe like a drop of the water. So in order to have a good system for general system for all the system in water in Indonesia, we need to have like 3 different parts. First, you need to have the ceramic, and then we need to have the absorber, we need to have the membrane. Ceramic we can use for the pre-filter, we can remove the dirty, or we can use the absorbent to remove the odor, to remove the chemical in the water. And then finally we can use the membrane to clean all the water after they already been processed by using the ceramic and also by using the carbon. So every method they have good and bad. So we have to combine them into one single system. Thank you.
Is there any more question from the audience? Not yet. One more question from me then. While we wait, if I'm not mistaken, Dr. Brihandana, you said that this membrane can also be used to filter gas. So for that purpose, can we also use spiral wound module?
Okay, the spiral model that I explained previously is for the water. If you want to, the membrane is different. Water membrane, gas membrane, and blood membrane is very different. So the simplest one is the water membrane because it's only like a microfiltration, filtration membrane. For the gas, we need to do some little bit modification, very difficult one, also very expensive one. So as far as I know, the gas membrane is coming from the water membrane, and then they do some like coating on the surface of the membrane. It's very expensive and very expensive, and we need to hire equipment to do this one. And then also this one is very sensitive because it uses coating very thin film on the membrane surface. When we not carefully roll the membrane, the spiral will damage the surface. And also making spiral module is much easier, much cheaper compared to the gas module because based on our experience when I work in Japan, so we need to, in order to make the spiral module for the gas, we need to send the membrane to US. It costs around 10,000 USD for one single module. It's very expensive one. And then the material to make the membrane also very expensive. So maybe the question is also like, is it possible to use the water membrane for the gas or gas for water membrane? It's kind of different also to different applications. Gas membrane is based on the solution diffusion mechanism. Water membrane mostly based on the molecular sieving mechanism. So the process is different. Of course, we can use the water membrane for the gas or the air purifier, of course we can use that, but we cannot use the water membrane for the gas. Like we cannot use water membrane to spread it between nitrogen and oxygen. We cannot do that. But also we cannot use the gas membrane for the water membrane because it takes a lot of high pressure to push the gas and push the water go to the membrane for us. So yeah, it's kind of different, and also it's more expensive when we are talking about the gas spiral model.
Okay, we have another question from Muhammad. I'm sorry, Muhammad Kalimanjaro.
Okay, so yeah,
A question regarding the biocompatibility of the silver nanoparticle. He found that silver nanoparticles have been used in daily products such as clothing, towel, utensils. What if the silver nanoparticle enter our body? Is it safe or not?
yes, we know that silver nanoparticle is not safe for vampires, not safe. So is it safe for the human body? Yes, safe depend on the amount of the silver nanoparticle in our body. But I'm not the one who maybe the medical doctor they can explain better than me. But for this membrane, we only use like a 0.1% of the nanoparticle in the membrane. So it's kind of very small amount of particle. And some membrane will stay in the membrane. Some membrane will flush away and then go into the water that we consume. So I think it is still below the standard of allowable that we can consume. So yeah, I think it's still safe, but we never tried, but we need to try. Maybe we need to do some. Yeah, we need to do some like medical tests, how safe the water for the human body for the long-term process. But some people they already put something in the towel, and then they do some like in the food. Something. I think it's no problem. As long as we are not vampire, I think it's safe for us. As long as the amount of the silver is not much. Yeah, that's my opinion.
We have another question from Bintang Aji. If we apply the coating on the membrane filter, like maybe AGNP as electrostatic absorption and microbial properties, is there any possibility so that the coating kind of break from the membrane, and the coating in this case, AGNP itself will contaminate the water?
Yeah, thank you for the question. We didn't do this kind of research, but I read some paper. They did some research of this. So they checked the permeate waters coming from the membrane. So they make the membrane, they're adding the additive into the membrane, and then they do the test, and then they check the permeated water, is it safe or not. So they did the test, and some of the silver flush away and then go into the permeated water. But it's possible if it can contaminate the water if the amount of the silver is in very high concentration. But I think in this case, we just only use like 0.4% maximum. So I think it's still not that dangerous for the water itself. I think. Yeah, that's my opinion. Thank you for the question.
5 minutes. Start from 10 until 10:45 GMT plus 7. Please join again at 10:45 GMT plus 7 for plenary session 2. Thank you. Okay. Thank you, Dr. Gunawan Setia Prihandana, for the great talk and presentation. And also thank you, Ms. Rizky Astari Rahmania. We are delighted to welcome PT Lab Sistematika Indonesia as Icatam 2022 partner to give an incredible video presentation. And we will have a break session for 45 minutes, start from 10 until 10:45 GMT plus 7. Please join again at 10:45 GMT plus 7 for plenary session 2. Thank you.
Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi.
Ladies and gentlemen, welcome back to Icatam 2022. In this session, we would like to invite Professor Kim Lim from Kumon National Institute of Technology to deliver the second plenary session, moderated by Mr. Iksanul Kauli, MNG. Professor Kim Lim and Mr. Ali, the stage is yours.
Okay, thank you for the occasion. Good morning, ladies and gentlemen. I'm so honored to be here at the International Conference on Advanced Technology and Multidiscipline, or Icatam 2022. So, I am Ali Iksanul Kauli as the moderator for this secondary plenary session. In this session, we will learn from our honorable keynote speaker, Prof. Kim Lim from Kumon National Institute of Technology, Gumi, South Korea. So, before we start the session, I would like to briefly introduce Prof. Kim Lim to the audience. So, he graduated his bachelor degree in mechanical engineering from Kumon National Institute of Technology. And he gained his master and his PhD degree from Biomedical Engineering, College of Medicine, Seoul National University, South Korea. After finishing his academic studies, he did some postdoctoral research activities in Department of Mechanical and Biomedical Engineering, Gangwon National University, Chuncheon in South Korea, and also in Department of Biomedical Engineering, Johns Hopkins University, Maryland, United States of America. Now, he is the professor in the Department of Medical IT Convergence in KIT. So, in this second plenary session, the topic for his talk will be physiome-based in silico research in pharmacology or medicine, deterministic and stochastic model. So, the time session for this session will be 60 minutes. And Prof. Kim Lim, the stage is yours.
Hello, thank you, Ali. Good morning. I'm Kim Lim from KIT, South Korea. So first of all, I'd like to thank to the ICAT AM committee and organizer, including Ali, for having me and giving me a chance to deliver my talk. And I want to congratulate for holding the second international conference, ICATAM, to the committee and the organizer. So shall I deliver the talk now?
Sure, Professor.
Okay, so let me share my screen. Can you see my screen?
Yes, it is clear, Professor.
Okay, so I will start. So my talk is about physiome-based in silico research in the field of pharmacy and as well as medicine, which I have been doing so far. So in the meantime, two main approaches to develop in silico system, such as a deterministic and a stochastic model will be introduced. So here's what I'm going to talk. First, I will introduce structure of the cardiac physiome model, which we have developed so far. And second, application of cardiac physiome, such as a drug cardiac toxicity evaluation and cardiac arrhythmia. So first, the structure of cardiac physiome model. So the goal of the physiome is to develop a strategy and the methods for integrating vast amount of biological function information. So far, we have suggested a methodology to integrate the biological function and data as much as we can obtain in worldwide. Though there are still lack of data and the lack of a mechanism which we have to reveal. Therefore, we have developed a cardiac fusion model, particularly cardiac fusion model in order to use to predict a specific biological function and drug responses and apply medical devices and the pharmaceutical industry. So among hierarchy of biological system from DNA to organism, this is a range of genomics and proteomics, which are study of structure and the function of gene and the protein respectively. Here, the range of the physium, especially for cardiovascular system, is from between the part of protein and cellular level to organ and organism level. So microscale here is represented with a Markov model of subcellular molecular kinetics, which is mathematically formulated with several ordinary differential equation, which is called a lumped parameter model. Macroscale here can be represented with, for example, electrical conduction model, which is mathematically formulated with several partial differential equation, considering both time and the space at the point of continuum mechanics point of view. Here, the cardiac muscle is electrically excitable and also mechanically excitable. So we have to formulate it with the electrophysiological point of view and also mechanical point of view. So in the microscale here, the ion channel is formulated based on the Markov model, which is based on the chemical reaction between state and the state. And this, so this can be formulated to whole different type of ion channel, ion pump, and exchanger. So if you integrate them all and incorporate them to the cellular membrane here, then you can simulate a cellular response in terms of electrophysiological point of view. For example, ionic movement across the membrane and the membrane potential, shape of the action potential, things like that. So single cell model is constructed based on the mathematically ordinary differential equation. And in the macro scale, we can make the electrical conduction model based on the continuum mechanics point of view. So we solve the conduction equation passively, then we incorporate active electrophysiological cellular model to the 3D model here. Then you will implement and simulate electrophysiological model of whole heart. In same manners, you can the electrical potential in the heart reflected to the body surface, then you calculate conduction through media inside your body. Then you can calculate body surface potential. For example, cardio-electrocardiogram. And in the mechanical point of view, you will make the cross-bridge mechanism in a myofilament model is triggered by calcium signaling from the electrophysiological model, and you simulate cross-bridge model, and also in the macro scale, you will simulate based on the constitutive law and the stress equilibrium equations and under the hyperelasticity material property. Then you incorporate cross-bridge model into the mechanical hyperelastic model then you can simulate pumping heart, and which pump the blood, and the blood pumped through the artery. Then also the hemodynamics is coupled. So based on the Navier-Stokes equation, you will calculate and simulate hemodynamics as well. So this is a whole schematic of for the cardiac physium at the moment. So in the here, 3D heart models contains electrophysiological cellular model, which contains subcellular molecular kinetics, including all kinds of membrane protein, as I said before, and intracellular protein being involved in the cellular electrophysiology. So normally, the 500,000 to 1 million cellular model is incorporated and distributed to the whole ventricles in order to obtain the reasonable response of ventricular electrical propagation. So this is the governing equation for the electrophysiology model of a single cell. And here's for electrical wave propagation through cardiac tissue, we adopted a biodomain model, which contains a reaction diffusion equation in two domains, such as intracellular part and also extracellular part, which is called interstitial space. So we calculate both of intracellular space and the interstitial space at the same time. So this is the reaction diffusion equation in interstitial space, and the second, this one is that in the intracellular domain. So left side is a diffusion term in a passive electrical conduction, and the right side here explains a reaction term based on the single cell electrophysiology. Secondly, here the cardiac mechanics model, at the mechanical point of view, considered micro scale and also macro scales. In the micro scale, the molecular kinetics for the cross-bridge mechanism, which is formulated by employing a stochastic Markov model, considering troponin, tropomyosin, calcium signaling, and things like that in order to predict amount of active tension generation based from the myofilament. In the macro scale, here, 3D heart mechanical model is implemented by formulating with the equilibrium law and the constitutive law of hyperelastic material property for soft tissue model. So stress equilibrium equation and constitutive laws, we calculate together, then you will get stress distribution, strain, and displacement, force, and active tension, and deformation of the heart. So this schematic represents how we implemented excitation and the contraction coupling of heart. So left part is electrical point, and the right part is mechanical component. Among two parts of electrical circuit here. So this electrical circuit represent electrophysiological model of a single cell. So that is embedded, incorporated into each of the node here. Okay. So this electrical circuit model represent cellular electrophysiology. So here the resistance represent ionic channels, and the battery represent non-slip potentials. Arrow here, current source represent ionic pump. So resistance, which explain the ionic channel, is not a constant. This is consists of several ordinary differential equations, which are formulated by experiment in the protein level. So in the right, the cross-bridge dynamics here, which is incorporated to the 3D cardiac mechanical model. This is also connected to the long-term model of a vascular system here in order to give the boundary condition of intraventricular pressure to the ventricular wall. So here, so there are three physics. This is a macro model of cross-bridge, and which is ordinary differentiation. And this is a continuum model of hyperelastic FEM model. And outside here, the electric circuit is represent hemodynamic model. So these whole systems, we implement them all together, and we calculate them together, then we can get any physics of cardiac response, electrically and mechanically. So this gives you what we can obtain from the excitation and the contraction coupling simulation. We can obtain the action potential propagation through the cardiac tissue and the mechanical contraction as well. And all the responses in the microscale, subcellular level, such as states of all the protein subunits, all the concentration of electrolyte, and all the electrical current across the cell membrane. So this is the architecture of in-house code software in our labs, thanks to the Aroli, Marcellinus. There's a pretty big international database from the in vitro assay and cellular and tissue experiment named the CellML. So there are a lot of data from the experiment in the CellML, which are fully open. We have developed the CellML code formatter, which convert CellML format of the mathematical model into C++ code, which is suitable to our simulation system, named CEP cell here. CEP cell system contains all kinds of cellular model, all kinds of mutation model as a plugin, and all kinds of drug effect, which have been published so far. So from this, whatever you choose among them, so you can computationally simulate and obtain the response in a microscale level, cellular level. So action potentials and all the current, the state of a protein. Whatever you are curious about single cell models, you can get from this system. And from this, also this CEP cell system can be also incorporated into the CEP 3D system here. And you can simulate computationally and obtain the response in the macro scale levels, like the organ level response, and the electrical propagation through the heart, and the virtual ECG waveform, and the body surface potential, like that. So for the validation of the virtual heart in cellular levels, action potential shape from simulation were compared with the experimentally measured one for both the ventricle and atrial cell. In the macro scale, we simulate and obtain the electrical propagation through the atrium, ventricle, reflected to the lung, reflected to the body surface. Okay? And the virtual 12-lead ECG waveform. So the personalized virtual heart, we obtained and used the geometrical model of heart from the specific patient, and considering the placement and the location, direction of a heart inside a torso as well. Then we found that the virtual ECG waveform was quite similar to with the real ECG waveform, having only 5% error. So So far I have explained the structure of cardiac vision model, which we have already developed. From now, I'm going to deliver one of the application of cardiac vision model, which is for evaluation of drug cardiac toxicity. So in the background of that is evaluating the possibility of triggering cardiac toxicity of existing drug have limitations. So high risk drug causing cardiac arrhythmia, for example, have not been filtered out well during the new drug development stage. So this table is a list of drugs previously distributed in the market, but withdrawn from the market due to the tachyarrhythmia induction. So, and there are cases where the evaluation was wrong and cannot be distributed, even though it does not actually cause the cardiac arrhythmia. So appropriate evaluation guidelines need to be prepared to accurately determine the drug heart toxicity. Therefore, the American FDA established the 4-stage assay named the SIPA project to solve these limitation and the problem and evaluate the drug safety. So the 4 stage of the SIPA model is like that here. So first branch is in vitro assessment of drug effect in the multiple ionic current, which has to be done in the protein level PET assay. Okay. Second branch is in silico computer modeling to predict the risk. This computer model have to get the data from the in vitro assay in the first branch, so which is being explained, and this part is our research topic. And the second branch is in vitro effect on the human stem cell derived ventricular cardiomyocyte in the tissue or cell level experiment has to be done. And the in vivo ECG biomarker in a phase 1 clinical trial has to be done to be accepted. So 4 of the branch, okay, part of the experiment has to be done for the drug cardiac toxicity estimation. So, as I said, the cardiac vision model can be mainly used for the stage 2 here, which apply data obtained from the stage 1 into the model. So vision model obtained in vivo data from stage 1, as I said, and computationally simulate and provide a cellular response and organ response as well. So from the PET experimental data in silico simulation in cell level and organ level. So we simulate the shape morphology of action potential shape in a single cell level, and also we simulate the electrocardiogram. Both are very, very important for estimating the cardiac toxicity from the drug. To explain in more detail for each step, we first obtained the 2000 set of IC50 and the Hill coefficient, which is from the experiment using bootstrap, which is a way for uncertainty quantification of the raw in vitro data. This part, thanks to the Ali, has done create the uncertainty quantification algorithm, implemented it, and we use because of due to the limitation of experimental condition, we need to get the more reliable data from the experiment. So we did this UQ solution. And 2000 set of the IC50 and the Hill coefficient is calculated in the way are used as input for the in silico cell model according to the drug concentration here. Then we get cellular response under the drug. So we use the cellular response data from the simulation and classify drug toxicity by applying the machine learning approach from the cellular data, which is calculated from the simulation. So FDA research group provided QNet and QInward as a biomarker for drug toxicity evaluation with a logistic regression, while we provide more sophisticated algorithm such as artificial neural network and CNN, and we compare the performance between the FDA group and our group. So we got we did several machine learning algorithms, logistic regression model, and ANN and CNN. We trained them and we tested them with already known drug. So we got these scores. This system classified high risk drug group and the low risk drug group, and also intermediate risk group. So we got this this score, which is pretty good. And this is published to the journals under the when we use the artificial neural net. So we provide better performance than that FDA provided here. So logistic regression, which is done from the FDA, and the ANN from us. So we have the better score than the FDA group. So this is one of the reasons. This is the whole schematic. Explain the in vitro, in silico, and the artificial intelligence integrated platform. So experimental data and uncertainty quantification and single cell simulation and the machine learning together. Then once you do in vitro assay, then you will get drug toxicity prediction. Okay, so from now, I will introduce another application of a cardiac vision model related to the cardiac arrhythmia. Yeah. So yeah, I will explain briefly here. So this is about prediction of cardiac mechanical performance from electrical feature during the ventricular tachyarrhythmia simulation using the machine learning algorithm. So this is also, we do in silico deterministic simulation, and we get three-dimensional data, and we extract a feature from the data, and we use them to the machine learning. Then we predict mechanical performance. And this is about the computational prediction of effect of mutation named D172N KCNJ2 mutation on the ventricular pumping during sinus rhythm and the re-entry arrhythmia condition. And this one is about the virtual defibrillation simulation, which provide optimal defibrillating protocol. So we induce the tachyarrhythmia here, and we will apply the defibrillation virtually with a specific protocol here. then we we predict whether this protocol is successfully defibrillate the heart or not. So this simulator is used for the predict and obtain the optimal defibrillating protocol as well in the three-dimensional model. Okay, so yeah, so far I have introduced the structure of a fusion model first and application of fusion model in the field of pharmaceutical and medicine, cardiac arrhythmia. Now, I will briefly introduce machine learning research for the cardiovascular system, such as continuous blood pressure measurement and cardiac arrhythmia classification. So this is for the continuous blood pressure estimation using simultaneous use of ECG electrocardiogram and also PPG, photoplasmogram waveform. ECG has the information of how membrane potential propagate through the cardiac tissue. What's the action potential shape like? When to study, when to the depolarize and repolarize, and when to finish them, things like that. And the PPG has the information of what's the blood pulse shape like, and the time for the pulse transit time, things like that. From the both of ECG and PPG signal, we are able to extract important feature for estimating blood pressure, such as pulse transit time, pulse wave velocity, and stiffness of artery, things like that. However, we may not be able to know all the important feature for that. Okay, in the case, so we don't trust all the feature we can obtain, but we expect there are more features which are available. So we use the raw data, shape of the ECG waveform and also PPG waveform for the input to the CNN model. So we will rely on the CNN feature extraction protocol. So we give the difference of ECG waveform and PPG waveform, then which can have both of the feature from ECG and the PPG. So we use, as I said, we use the CNN, and also we adopted the bidirectional LSTM together. So as a result, we have estimated systolic and diastolic blood pressure continuously with quite good score using the standard scoring system. We got here, so this is our models, SBP and the DBP. It has the small standard deviations, and we got the A score. And last, this one is the cardiac arrhythmia classification. Concept is like from 12 lead ECG waveform, we classify 9 different type of cardiac arrhythmia. Cardiac arrhythmia has very many different type of cardiac arrhythmia. So important 9 different cardiac arrhythmia was classified by our machine learning algorithm. This workflow explained, first we got ECG signal, and we have R-peak detection, and we will get from R-peak to R-peak after 3 cycle. Then we get that 3 cycle signal as a group, segmented. Then we clustered several samples and as to one, and we use that final 3 cycle signal, process the frequency feature map, then we put it to the 2-dimensional CNN and classified 9 different arrhythmia. It was just we did this one several years ago from the competing cardiology challenge. So this is the result. So yellow is represent just case which are quite good. So atrial fibrillation and AVP, left branch bundle block, and the right branch bundle block. The 4 of the arrhythmia was classified quite good among the 9 arrhythmia, and whole weighted F1 score was 0.78. So it has been published in the journal. Yep, I think I introduced all of what we created so far, and I want to thank to all the member of a computational medicine lab here. And we got 5 PhD course student and 5 master student course. I thank to my members here. And they are also collaborators in South Korea and America and Italy, Japan. Yeah, thank you very much for listening my talk, and I apologize if I just explained not very clear, and so probably you may have many questions. Then I will answer you. Yeah, thank you very much.
Okay, thank you very much, Professor Kim Lim, for the presentation. It is very insightful, and we can learn a lot of new things over there. Before we start our Q&A session, I would like to summarize what Professor Kim Lim has presented into several points. First, the physiome-based model has the purpose of developing strategies and methods for integrating vast amount of biophysiological function information. And second, the structure of physiome-based model consists of the simulation of heart in single cell, as well as 2D and organ level at 3D simulation, both electrical and mechanical simulation. The third, the modeling of the heart simulation incorporates the use of ordinary differential equations, which explain cell and everything. And the application of physiome-based model can be various, such as predicting cardiac arrhythmias and drug toxicity assessments. And lastly, which is quite important, machine learning play significant role in the drug toxicity assessment and other application of physiome-based model by classifying of drug and arrhythmia. So I think there are several questions already from the audience. So if for the audience, if you have some questions, please raise hand, or you can put your question into the chat box below, and we can discuss. So there is one question already, Professor, from Miss Ilma Amalina. So I will read the question for you. Good afternoon, Professor. Since the research step is so complicated and require multi-steps, how long typically a research done for this kind of topic?
Okay. Yeah. I studied from when I started a graduate course, which was 2003, and I start to do in the physium research from that, and I didn't start from nothing. Okay, I have my supervisor was really actively doing the electrophysiology model, and we start from that, the two-dimensional bidomain model. We start from that, and and that field was worldwide, is not very popular, but in the specific countries, for example, United States and New Zealand and England and also Japan, who has a very big fund for that. So during my course, I did that, and also after I graduate, after I got the PhD, I moved to the more special lab for the physium in the Johns Hopkins, and I joined that, and I start to program the mechanical physium model, and I incorporate the electrical model and the mechanical model, just one-way signal, calcium signaling. But the other part is they do both interaction. So that's what I have done so far. Yeah.
Okay. Thank you very much, Professor, for the answer. So for the next question, I think we are still waiting. So I have some question actually, Professor. Let me ask some question for you. Maybe in the computational study we have you did with the group computational studies, computational simulation, but the important thing is that we have to predict what clinical practice happen in the real practice. So how do we validate like our result with the clinical practice in the hospital or in other medical lab?
Yes, that questions, I got that question all the time, wherever, so whenever. So that's the most difficult one, because we have limitation to measure that. We have limitation to do experiment, so it's very hard to satisfy all the people from the model. Yes, but what we do, I will tell you what we do. Just we will get the model is just constructed based on the experimental data, 100% experimental data, which is done in the level of a protein level in the PET clamp. So so we have to do that experiment reliably, and but we don't do that as physiologists. All the physiologists in the world, they have done a lot of experiment, and I believe that. And we use I believe what data what we use is reliable. So based on that experimental data, we constructed a mathematical model. And 50% I believe that. And also, but we have to validate it. So we simulate in the single cell level. We can't validate all the mechanism, but we can validate doing the comparing the phenomena in the single cell level. For example, action potential shape. Okay, we simulate action potential shape, and we compare with the measured one. And also in the tissue levels, conduction velocity or things like that. And organ level, we can measure in the electrocardiogram or body surface potential. Okay? We can do that, and we can simulate that, and we can compare the phenomenological point of view.
Okay. Okay, thank you very much, Professor, for the answer. So there is one question from the chat box from Miss Sylvia Rahmi from Statistika Universitas Brawijaya. Good afternoon, Professor Kim Ulim. For the modeling, you use machine learning. Which one have the better result for the pharmacology and medicine topic? How to implement the model to the pharmacology industry? The machine learning, Professor.
Okay.
So which one has the better result for pharmacology and medicine topic? And maybe the important question is how to implement the model that your group has been done to the pharmacology industry.
Yeah, that's difficult question. Instead of telling you the answers, I would like to explain my opinion in the machine learning part, especially in the pharmacology and the medicine. So I think the simple machine learning is the better than the sophisticated one, which means if you have the stochastic model, right? It's a machine learning. Stochastically, we fit the data, right? So you have to get reliable data first, and second important thing is your rationale. I mean, your hypothesis has to be correct. Like we don't know if my hypothesis is correct or not. I mean, there should be correlation, strong correlation. If there is a strong correlation between the input and the output, then if you use the reliable data, then your machine learning algorithm doesn't have to be very sophisticated. So very simple machine learning algorithm with reliable data and clear correlation makes best result. So yeah, but in reality, it's not like that. So data is not reliable, and hypothesis, I don't know. I'm not clear that's whether this is a very good or not. So the machine learning process is to prove my hypothesis. So I don't know if my hypothesis is very strongly clear or not. So in reality, you don't have the clear answer of that. So I think I would like to do my best for collecting reliable data and reliable feature and apply appropriate machine learning algorithm, whatever simple or sophisticated. Yeah, that's
okay. Thank you very much, Professor. So basically, for machine learning, we need to have as simple as possible. The model has to be as simple as possible to be able to implement it in the industry, and also we rely on very reliable data, which is quite difficult to gather, and strong hypothesis, which is strongly related to clinical observations. Okay. Maybe there are some questions again from this from the audience. We are, if not,
I
have.
think,
okay.
Sorry, I think I didn't answer the second question in. Sorry.
To implement, yes, to implement.
Yeah. Yeah, that's until 5 years ago, I didn't have any idea to use my vision model to the pharmaceutical industry. But yet in the vision range of vision is kind of close to macro scales compared to the proteomics and the genomics. But the drug industry is experimented in the very small in the proteomics level. Okay. So it's very hard to connect proteomics data to the vision data. Okay. So it was hard, and but it is hard, but we can start anyway. Even though that's not 100% satisfiable. Okay. So the Toxicology Institute in the Korea, they suggested to apply the drug experimental data to the vision level. So we just use a very simple feature from the drug industry, which is called IC50, and the HIL is a characteristic of the drug in the cardiac cell. So we use that data to the vision model. So yeah, so far we can only use that data, but in the future and we can get more data measured, then we can adopt more data, more reliable data to the vision model, then vision model's result may be more reliable.
Okay. Okay, thank you, Professor, for the answer for the second questions. So I think okay. I have one last question, Professor, because the time is limited now. So like drug toxicity assessments seems to be a promising topic to be applied not only in pharmacy industry but also for patient itself, because patients sometimes need to understand the risk of what he consumes. So, and because the patient sometimes has different response to other patients because different condition. So is it possible from the physiomap-based model perspective that we build the patient specific model to help patient get healthy from the disease he occurred?
Okay, so your question is, can we make patient specific vision
model? Yes, Professor.
Yeah, that's also very, very important. And as I presented before, it's I just for the patient specific model, we just get the exact shape of a patient heart domain and location and placement of the heart, and but in the cellular levels, we didn't adopt anything else. But for the patient-specific models, we can adopt not only the geometrical information, but also in the functional and in a chemical information for the patient. Yes. So, as I said before, that's a limitation of the physiome. Range of the physiome is a kind of part of protein level to the macro scale. So, but we don't have a strong mechanism to connect to the lower level, I mean the protein level. So our blood test information, when you go to the hospital, you do blood test and you do the ECG measurement, and the hospital take a lot of information from you. Okay, yeah. But we can't use that database to our model at the moment because our model doesn't cover most of the data from the hospital. So has to be more studied in not computational research, but experimental research has to be done much more, then has to provide much more data, then computational research will be improved. So yes, experimental data is most important.
Yeah. Okay. So the key point is that the collaboration with the hospital and experimental guide is very important in order to improve the model itself and the prediction and the use of the model. Okay, we have no more question, I think. Before, I think this is the end of the session, but before that, I need to inform the participants to fill the attendance link in the chat box. You can fill the attendance first, and then there is a certificate of appreciation from the committee to Professor Kim Lim for giving the speech today. The committee, please to provide the certificate of appreciation. Okay. This is the certificate of appreciation for Professor Kim Lim as the keynote speaker for Icatam 2022.
Thank you
very much. Yes, thank you very much, Professor Lim, for giving such an insightful talk. And I think I can end this session, and I will give back to Master of Ceremony for the next session. Thank you very much for attending this session, and goodbye.
Goodbye. Thank you. And hopefully see you in the next year, third conference. Yeah.
Yes, thank you very much.
Udah. Thank you, Professor Kim Lim, for the fascinating session, and thank you, Mr. Ali Ihsanul Kauli. For all participants, we would like to inform you that we have another break session for 75 minutes that start from 11:45 until 13 GMT plus 7. Please join again at 13 GMT plus 7 for a plenary session 3. Thank you.
Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi.
Wes ketemu durung? Halo. Udah ketemu?
Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi.
Ladies and gentlemen, welcome back to Icatam 2022. In this session, we would like to invite Professor Tomoteru Fukumura from Tohoku University to deliver the third plenary session, moderated by Dr. Prastika Krisma Jiwanti. Professor Tomoteru and Dr. Prastika, the stage is yours.
Okay, thank you very much. Okay, good afternoon, everyone. So welcome to the second International Conference on Advanced Technology and Multidiscipline Universitas Airlangga. So we have the Professor Fukumura Sensei today. Fukumura Sensei, he's here. O genki desu ka? Konnichiwa.
Konnichiwa, good afternoon.
Okay, konnichiwa. So welcome to Universitas Airlangga. Unfortunately, virtually, but we hope that maybe someday we can invite you here to directly come to Universitas Airlangga Surabaya. So, なんか私5年ぐらい日本で住んでいました。2014から2019まで日本で慶応大学で電気科学を勉強しました。だから I'm very happy to welcome you here and I'm very happy to meet a Japanese professor today. So before we listen his talk, I would love to introduce Fukumura Sensei. So Professor Tomoteru Fukumura, or maybe I can call Fukumura Sensei, is a professor from the Department of Chemistry and also from the world premier International Advanced Institute for Materials Research, Tohoku University, Sendai, Japan. His expertise is in superconductivity, mainly to construct scientific foundation to discover, create, understand various solid materials from nanosize to microsize. He received his PhD in superconductivity from the University of Tokyo, Japan, supervised by Professor Koichi Kitazawa. He also received many awards, for example, from GSAP Award for the most promising young scientist, and also the Young Scientist Prize, the Commendation for Science and Technology by the Minister of Education, Culture, Sports, Science, and Technology, and also from GSPS Prize by Japan Society of the Promotion of Science, by the invention of magnetic oxide semiconductor. So I believe that Professor Fukumura is an expert in superconductor material. And also he published many publications, for example, in rock salt type PRO epitaxial thin film as a weak ferromagnetic condylattice. So his talk today is about materials exploration of metastable superconducting and magnetic oxide. So Fukumura Sensei, are you ready? So you have about 30 minutes to talk. Okay, so time is yours.
Sorry, how much can I have a time? How much time can I have?
I think it's about 50 minutes.
50 minutes. Okay, thank you.
Okay.
So, good afternoon, everyone. So, my name is Fukumura from the Tohoku University, and my major department of chemistry, and also I belong to the several institutes of the Tohoku University. And first of all, I would like to thank organizer to give me this opportunity. So now still we are suffering from the COVID-19, but I believe that I can visit your country in the near future. Okay. Okay, before going to my talk there, I would like to introduce my institute. This is Japan, and probably you know the place of the Tokyo. And our university, Tohoku University, is located at the Sendai city. This is the northeastern part of the Japan. And this is some photograph of our campus. This is the urban area of the campus. And in my department, My department is located the mountain area. This is some photograph, and sometimes we can see snow in winter season. And this is my colleague. So we have many colleagues in the Tokyo University, like these professors, and also we have some colleagues in the University of Tokyo, and Tsukuba and Ibaraki University and Tokyo Tech, and Naga Institute Tech. And these are the Japanese institute, but also I have a colleague in university, Dr. Tata Amrila. Until recently, he stayed our group and he was studying some oxide. I will talk about that. First, I have two topics. And the first one is Nictogen square net layered oxide. This is a new superconductor. And I will show you what kind of a superconductor is obtained. And the second topic is concerned with rare earth oxide. Probably most of us know that the rare earth oxide is an insulator, but recently we found electrically conducting rare earth oxides. And some oxide is a ferromagnet and some oxide is a superconductors. So I will show you some recent results. The first one is a Nictogen square net layered oxides. This is a chemical formula, so bismuth oxide or antimony oxide. So this is a crystal structure, so that this is a bismuth or antimony square net. This is a top view, and this is a rare earth oxide layer. So this is a same crystal structure. So in this case, bismuth square net is electrically conducting, and the valence is negative valent. This is an unusual oxidation state. And this rare earth oxide layer is an insulating layer. And this structure is similar to the iron-based oxides, iron-based superconductor, high-temperature superconductors. In this case, this square net is barium 2+, so this is the insulating layer. And this layer is iron arsenic layer. This is a superconducting layer. So in a sense, this is opposite. So this part is electrically conducting and this part is insulator. And this layer is an insulator, but this layer is a superconducting layer. And about this compound, previously the Professor Hosono's group reported that this compound is electrically conducting. So if the rare earth is small, so bismuth bond length is shorter and this interlayer spacing is shorter. So in this case, this resistivity decreases with temperature. So this is a metallic conduction. And by changing the rare earth oxides, so for example, the largest lanthanum, this becomes insulator like this. So by changing the type of the rare earth elements, we can control the electrical conduction. This is, in other words, this is a chemical pressure by changing the rare earth oxide, rare earth elements. And previously, this compound was reported to be not superconducting. But after that, we discovered that this compound can be a superconducting by introducing the excess oxygen. So if there is no excess oxygen, resistivity is not zero. But by increasing the excess oxygen, resistivity finally becomes a zero resistance like this. So, and with increasing the excess oxygen, this superconducting transition temperature increases by that. So indeed, this compound is superconducting, and this is a temperature dependence of the magnetization. And we can also observe the this Meissner effect. This is some proof of the superconductivity. So this compound is the superconductivity around 2 Kelvin by introducing the excess oxygen by using oxygen intercalation. So this is a lattice constant of this compound. The a-axis means correspond to the bismuth bond length. This is constant regardless of the amount of the oxygen, excess oxygen. But about c-axis correspond to this interlayer distance. By increasing the amount of the oxygen, the c-axis increases rapidly, and after that, this compound is superconducting. And this is a p-type conductor, but the whole carrier density is almost constant regardless of the amount of the oxygen. So this is a summary. So this is c-axis length. So c-axis length increases with introducing the oxygen, and at threshold, this becomes superconducting like this. So the longer c-axis lengths correspond to the emergence of the superconductivity. So this compound is a yttrium-2O2 bismuth, and we try to anyhow this is a summary of the some representative high temperature superconductors. So for example, this is a perovskite copper oxide. So in this case, in case of the X equals 0, this is an anti-ferromagnetic insulator, but with doping the strontium, this is a whole dopants. So, and finally, this compound becomes a superconducting. And in this case is a nitride chloride layered compound, this one. In this case, a pristine compound is insulator, but by introducing by intercalating the lithium metal, resistivity decreases and the superconductivity appears like this. And in this case, this is Y2O2 bismuth. In this case, there is no carrier doping. So excess oxygen is not related with the carrier doping. But by introducing the oxygen, c-axis increases and finally superconductivity appears. So this compound is a little strange because the superconductivity is induced by not carrier doping like this compound, but the increase of the c-axis length. So this is just a geometrical change of the lattice constants. Anyhow, this bismuth square net superconductivity is this is observed for the first time. So there are the various bismuth square net compounds, but some of them are not superconducting. There are some superconducting compound. This superconducting emerges because of the palladium bands at Fermi level. So we try to make other layers compounds by using the similar method. So in case of the yttrium-2O2 bismuth, this oxygen intercalation is very easy. So by introducing the Y2O3, amount of the Y2O3, we can introduce an excess amount of the oxygen. And this is easy, but for other layers, oxides bismuth, this is not applicable because excess oxygen is difficult to be introduced in these compounds. So we use calcium oxide as a new oxidant. So this is indeed a strong oxidant. And by mixing the calcium oxide, this calcium oxide oxidizes this compound by introducing excess oxygen, and the calcium metal is gone by the evaporation. This is schematically shown in this figure. So the calcium oxide is used for the oxygen integration for the various layers to oxides bismuth. So as a result, we can succeed in oxygen integration in various areas of bismuth. So this is a summary. So this is the temperature dependence of the resistivity of also bismuth. So this is a pristine also bismuth. In this case, terbium to also bismuth. So this is not superconducting, but introducing the excess oxygen, this becomes this is a zero resistance. So this is a superconducting. In case of the dysprosium, this is also the superconducting by oxygen integration. And this is yttrium. So yttrium is in pristine state superconducting below 2 Kelvin, and this superconducting transition temperature increases by oxygen integration. And also these erbium and lutetium, the superconducting transition temperature increases by oxygen integration. So interestingly, this terbium and dysprosium and erbium and lutetium, this is not lithium, but these are the antiferromagnetic compounds in pristine state. So in such a magnetic compound, the superconducting temperature is significantly decreased, but as you can see, the TC, superconducting transition temperature, is the same as other compounds such as non-magnetic white salt bismuth. This is at present, I don't know what's going on, but this is some interesting properties of these compounds. And this is a summary of the superconducting transition temperature. Superconducting transition temperature is always around 2 Kelvin by oxygen integration. And for all of these compounds, the C-axis length is different, but by oxygen integration, the C-axis length increases. And finally, the superconducting transition obtained like this. And this is shows an interesting feature. So this is a C-axis length, but this is a C-axis length divided by the A-axis length. So this is a kind of the aspect ratio of the unit cell, or in other words, this is the tetragonality of this compound, of the unit cell. So for all of these compounds, at the threshold of the same threshold of this tetragonality, the superconductivity emerges like this. So if C over A is over 3.42, the superconductivity emerges like this. So this superconductivity is more or less a tetragonality induced superconductivity, not carrier induced superconductivity. And this is one exception. This is a no superconductor. This lanthanum CO2 bismuth, this lanthanum is the largest ion, so the bismuth bond length is longer, and bismuth square net and interlayer spacing is the largest. So as a result, this is a semiconducting or insulating conduction. But by conducting the oxygen integration, the C-axis increases, but this resistivity decreases like this. And this is not superconducting, but this is highly electrically conducting. So, and this whole mobility is relatively high. So, this is not single crystal, but polycrystal, but this whole mobility is relatively high in comparison with other oxynuclide or oxycalcogenide. These are the oxynuclide and oxycalcogenide polycrystals, various polycrystals. And this is a mobility, carrier mobility, and this is a hole density. So most of them shows high hole density, but low mobility. But this compound shows high hole mobility. This is comparable with host compound of the iron-based superconductor. So this compound, some of this compound is superconducting except for lanthanum, but this lanthanum CO2 bismuth also interesting from the viewpoint of the electrode materials. And previously, we performed the oxygen intercalation by using the high temperature, such as 1000 degrees or something. And this high temperature sintering often resulted in formation of the impurity phase. So we were looking for the some more efficient oxygen intercalation method at the lower temperature. So this is one of the low temperature topographic oxidation method. We use this zirconia doped cerium oxide as a solid state oxidant. So we just sinter this compound and this compound. This is separately placed in same quartz tube. And we heat this compound and this compound in a quartz tube. So this is some XRD pattern of this compound and picture of this cerium doped this zirconia. And above 200 Kelvin, this compound is changed more or less. And as a result, the oxygen is supplied from the cerium doped zirconia to this compound. And finally, we can obtain this compound, excess oxygen in this compound. And this is a result of the superconducting transition temperature. So in the previous method, we use 1000 degrees sintering temperature, but by using this solid state oxidant, we can increase, we can obtain the superconducting Y2O2 Bi flow above the 200 degrees C to 800 degrees C. And by using this method, we can obtain high pure superconducting compound like this. So anyhow, this is also known as oxygen storage material. This compound can be used for the solid state oxidant at low temperature oxidation. And this is this experiment is related, concerned with bulk polycrystal, and also and we tried, we performed the oxygen intercalation, but also we tried to dope lithium, fluorine, or hydrogen in place of instead of the oxygen. So lithium is indeed intercalated in this layer, and fluorine and hydrogen substitute the oxygen like this. This is a fluorine ion and hydrogen ion is this is an anion. And as a result, we obtained also the superconducting white O2 BI. This is not oxygen intercalation, but lithium intercalation or fluorine or hydrogen doping. And actually, we can obtain a higher superconducting transition temperature in case of the lithium intercalation or the hydrogen doping. So in this compound, the oxygen intercalation is not necessary factor to obtain a superconducting emergence of the superconductivity. And still this tetragonality dependence seems to be applied for this emergence of the superconductivity. So this is all these results is experiments of the bulk polycrystal. So next, we try to make a epitaxial thin film of this compound by using the pulsed laser deposition. Pulsed laser deposition is this is some starting materials, and by irradiating a pulsed laser, then we can evaporate this starting materials, and finally we obtain the thin film, epitaxial thin film. In this case, as I told you, this bismuth is unusual valence. This is a 2- ion. And so by using this method, always we obtain not this compound, but the bismuth, trivalent bismuth of the white O3. This is also the very stable compound. So anyhow, it is difficult to obtain a negatively divalence bismuth by using this pulsed laser deposition, even in ultra high vacuum. So we developed a different method. This is the first generation solid phase epitaxy. So at first, we feed bismuth and yttrium powder, and the bismuth powder and yttrium powder react to each other. And after that, the secondary, we feed this bismuth yttrium powder and this amorphous white O3 on calcium fluoride substrate. This is a single crystal substrate. And finally, we obtain white O2 bismuth epitaxial thin film. This is the XRD pattern of this thin film, and XRD peak is very small. So this means this crystallinity is not so sufficient. And after that, we developed a multi-layer solid phase epitaxy. Now, this is a starting compound. So by using the sputtering, we made a multi-layered precursor. This is white O3, and this is yttrium, and this is a bismuth. So that this is a multi-layer of the bismuth and yttrium and white O3 layers. After that, we hit this multi-layer inside. And as a result, we can obtain a white O2 bismuth epitaxial thin film. And this is XRD pattern. So in comparison with the previous method, we can obtain a much higher crystalline epitaxial thin film of this compound. So we obtained this epitaxial thin film. So in comparison with the bulk polycrystal, this white O2 bismuth shows higher electrical conduction because this is a single crystalline. Also, this epitaxial thin film doesn't show a superconductivity. So this is similar to the pristine white O2 BI. Probably there is no excess oxygen in this compound. And also we try to make a similar antimony square net compound. So in this case, we can successfully obtain this epitaxial thin film. So in the previous report from a different group, bulk polyester was reported. This is a highly insulating conduction. This is a conduction is almost very small. But by making the epitaxial thin film, we can obtain a highly conducting LHO2 antimony, this compound, like this. So the resistivity is 4 order of the magnitude or 5 order of magnitude different. This shows a much lower resistivity in comparison with the bulk polycrystal. So the reason is not so clear, but this compound is known to form the charge density wave. Charge density wave is one main reason to be insulating. So it is possible that this is epitaxial thin film. So by from the epitaxial force, this formation of the charge density wave could be suppressed. Anyhow, this is probably the first report of the highly conducting the antimony scarlet compounds. So next, we would like to move to the different compound. This is a very simple compound. This is a binary compound and rare earth oxide. But this is some of them is new solid phase, and some of them are some interesting properties. And in this case, this compound is only thin film, epitaxial thin film, because this is a metastable phase. And by using the epitaxial force, such a metastable phase can be stabilized on a single crystal substrate. This is a schematic of the pulse laser deposition I told you. So this is a ultra high vacuum chamber, and this is a starting materials. And by irradiating ultraviolet strong laser, this is a ultraviolet laser. So this photon energy is very high. So in a temperature scale, this is 60,000 Kelvin or so. So by focusing the X-ray laser, many compound is easily evaporated like this. And finally, we can obtain a thin film. And for thin film growth, we also use infrared laser for heating. This is a very convenient method to obtain a high temperature, such as 1,000 degrees C or so. And so this is some photograph of the evaporation. So this is a invisible laser, ultraviolet laser, and this is evaporated species from the starting compound. By this merit of this method is it is possible to obtain metastable compounds because this is not thermally equilibrium state, but a kinetic state. And also there we can obtain highly pure thin films because this is ultra high vacuum. So this is a very old story. So for example, this is titanium oxide. For example, the anodized type titanium dioxide, very famous for the filter catalyst. But by using the pulse laser deposition, we can heavily dope the cobalt. Cobalt is some magnetic ion in this TiO2. And this cobalt is heavily doped, but this is not this cobalt doesn't form the impurity phase, but this cobalt is solved in the titanium dioxide. So that, in other words, cobalt substitute the titanium site like this. And this is a trans TEM image, so atomic release of the TEM image. And this cobalt doped titanium dioxide is shows a very, very high Curie temperature. This is more than 500 Kelvin. The maximum is 600 Kelvin. So this is very high in comparison with other well-known ferromagnetic semiconductors. And this is a semiconductor. So by using the field effect, we can increase the paramagnetic state to the ferromagnetic state. This is an anomalous Hall effect. And this corresponds to that by introducing by applying the electric field, this magnetization increases from 0 to finite. And this is a first demonstration of the electrically induced room temperature ferromagnetism. And next, we move to the recent topics, rare earth oxide. This is well-known rare earth oxide. This is a chemically stable rare earth oxide. And most of them are denoted as R2O3. For example, the gadolinium 2O3 and dysprosium 2O3 and holmium 2O3 or something. And these are the, most of them are paramagnetic or anti-ferromagnetic at very low temperature, or some are diamagnetic. And most of them have a very large band gap. So this is a band gap is a very large, so that this is highly insulated. And this is chemically stable and almost no magnetic and wide gap and high dielectric, high permittivity insulators. And on the other hand, today we talk about the rare earth monoxide. This is not R2O3 but RO in a chemical formula. Many years ago, some compounds are reported. This lanthanum and cerium and praseodymium and neodymium and samarium monoxide. This compound synthesized by using the high pressure synthesis. And this is the bulk polycrystal. And after their report, no study has been reported. And this European monoxide, this is a very famous ferromagnetic semiconductor. So the single crystal and the epitaxial thin film can be obtained. And this ytterbium monoxide, this was reported to be some polycrystal or polycrystal thin film has been reported. And this compound is metallic conduction. And for example, about the yttrium monoxide, this was known to be a gas phase. This is a gas. And in this plume, there is a yttrium oxide gas molecule. This is not solid. And the other rare earth monoxide also they are known to be only a gas phase. And this is a Y2O3. This is a stable compound, and this is a big byte structures, and this is transparent because of the wide band gap. And this is completely insulated. And this is slides previously I showed you. This is a Y2O2 bismuth thin film. But during this experiment, we found that some amorphous Y2O3 becomes not transparent but black. There is, of course, no black Y2O3. So I thought that there is some new compound in this amorphous Y2O3 thin film. And after some investigation, we found that this black yttrium oxide is yttrium monoxide, like this. This is the first solid phase of the yttrium monoxide. This is also the epitaxial thin film on the calcium fluoride substrate. So this metastable compound is stabilized by epitaxial force from this substrate. The starting material is a Y2O3, but by using a pulse laser deposition, we obtained yttrium monoxide. And this is a rock salt structure. This is a transmission electron microscope image. This is rock salt structure. And we also performed the X-ray fluorescence photography. This is very useful for the element selective structure studies. And we found that this yttrium, divalent yttrium forms rock salt structures. So anyhow, this is a first rock salt yttrium monoxide, and this yttrium is divalent like this. This is a XPS spectrum, and there is some mixture of the trivalent yttrium, but this divalent yttrium is a majority. And this yttrium KH is in between the yttrium metal and Y2O3. So this is a signal of the divalent yttrium. And as I show you there, this Y2O3 is transparent, but this yttrium monoxide is not transparent like this. So this means that the band gap is very small. This band gap is about 5 eV, but this band gap is about 0.1 eV. And by changing the amount of the oxygen vacancy, so by increasing oxygen vacancy, the resistivity decreases. This is representative properties of some ordinary oxide semiconductors. And this resistivity is much higher than the resistivity of the Y2O3. So this is a conducting yttrium oxide. So after that, we extend to synthesize various layers monoxide. So next one is a cerium monoxide. This is there is a one 4F electron and one 5D electron. So in this case, this is a photoemission spectra, and cerium 5D orbital and the 4F orbital shows some strong hybridization. And this compound shows metallic conduction like this. And at very low temperature, the Kondo effect is observed. So interestingly, this whole carrier shows a very high mobility, more than 500 mobility. And also, at low temperature, the electron carrier appears. So that this is close to the semi-metal. So this is a heavy fermion paramagnetic compound. And the next praseodymium is also the metallic compounds. And this compound shows also the Kondo effect, and different from the cerium monoxide. This is a weakly ferromagnetic compounds like this, and the Curie temperature is about 28 Kelvin. Although the ferromagnetic hysteresis is very small. we can observe that both ferromagnetic magnetization and anomalous Hall effect. And another one is a neodymium compound. So this is a 4F3 configuration. So with increasing the 4F electron, the ferromagnetic ordering is strength. So this is also metallic compounds like this. And this shows clear ferromagnetic hysteresis and anomalous Hall effect like this. And the Curie temperature is 19 Kelvin. This is still low. But this Curie temperature is much higher than the neodymium chalcogenide or nictide. So this is a neodymium nictide and chalcogen. This is an insulator, and only a neodymium nitride shows a high Curie temperature. And the neodymium monoxide shows also the higher Curie temperature in comparison with this compound, and this is a ferromagnetic. And also this is a samarium. And this is a non-magnetic, but this is a heavy fermion system. This is also metallic conduction. And in this case, there are other samarium monochalcogenide, sulfide and selenide and telluride. These are the semi-conducting because the band gap is large. And for this compound, by applying the external pressure, this compound becomes a metallic. This is called as a golden phase. But in case of the samarium monoxide, oxygen is the smallest anion among them. So this smallest oxygen contribute to the chemical pressure in this compound. As a result, the samarium monoxide becomes metallic without external pressure like this. And this also shows a Kondo effect. So that this compound is also the heavy fermion system. And this compound is predicted as a wild semi-metal, but at present, I don't know this is a wild semi-metal or not. So next in periodic table, the next element is europium, but europium monoxide is a famous compound. So the next element is a gadolinium. This is also the 4F7. This is half-filled 4F orbitals plus 5D electron. So in this case, interestingly, so europium monoxide is a 4F7 5D0 configuration. In this case, the Curie temperature is 69 Kelvin. But the gadolinium monoxide shows a much higher Curie temperature. This is 270 Kelvin. This is much higher than the europium monoxide. And this is a summary of the Curie temperature of the various magnetic semiconductor. In case of the diluted doped magnetic system, Curie temperature is relatively high, but this is a diluted system, so the magnetization is usually small. In this dense ferromagnetic semiconductor, so for example, europium sulfide and monoxide and gadolinium mononitride, this magnetization is large, but the Curie temperature is low. But the gadolinium monoxide shows a much higher TC in comparison with other dense ferromagnetic semiconductor, and this is comparable to the TC of this diluted doped ferromagnetic semiconductors. So this is a very interesting compound for the spintronics, semiconductor spintronics. And recently, we reported terbium monoxide. This is more than half-shelled ferromagnetic semiconductors. And this Curie temperature is very large, similar to the gathering monoxide. And in this case, this temperature dependence of the magnetization shows strange behavior. So this is a Curie temperature. So at Curie temperature, the magnetization increases. And the magnetization monotonically increases, but around 20 Kelvin, the magnetization rapidly increases like this. So probably this is caused by the emergence of the magnetic sublattice of the 5D spin around here. And around here, this corresponds to the emergence of the 4F magnetic sublattice of the 4F spin. So probably this is a superposition of the temperature dependence of a magnetization like this. Such behavior is often observed in iron garnet. Garnet contains layers at A site and iron at B site. So the different atoms shows different magnetic sublattices based on the 4F magnetic sublattice and the 3D magnetic sublattice. But in this case, only single terabim atomic site shows formation of the magnetic sublattices of the 5D electron and 4F electron independently. This is an interesting magnetism of this compound. And this is recently reported the chromium monoxide. This is 4F10 configuration. So this compound shows a good electrical conduction, and this is electrical conduction can be tunable by changing the amount of the oxygen. So this is a kind of the oxide semiconductors. And this Curie temperature is also the relatively high, 130 Kelvin. And this study was performed by the Dr. Tata Murira of the University of Erlangen. And about ytterbium, ytterbium is almost nearly free occupied 4F orbitals. And in this case, this is non-magnetic, but this shows good electrical conduction, and this is oxide. This is also the one of the oxide semiconductors, and this mobility at room temperature is relatively high. So this ytterbium monoxide is epitaxial thin film and simple rock structure, so that this compound can be used for also the electrode compound. And lutetium oxide, this is a 4F free shell monoxide. This is also the oxide semiconductor. And the final one is this lanthanum monoxide. This is no 4F electrons, but 5D1 electron. This is a new superconductor. This is a resistivity, and the resistivity becomes 0 at around 4 Kelvin. And this superconducting transition temperature can be tunable by the electron density of this compound. And this superconducting transition temperature is much higher than lanthanum monochalcogenide. This lanthanum telluride 1.4 Kelvin, and lanthanum selenide 1.0 Kelvin, and lanthanum monosulfide 0.8 Kelvin. So this is a chemical trend, but this lanthanum monoxide, this is a chemical, from this chemical trend, lanthanum monoxide should show the lowest superconducting transition temperature, but this lanthanum oxide thin film shows the highest superconducting transition temperature. This is some irregular chemical trend. And all of these layers monoxide is rock salt structure like this. This is very simple. So, for example, this superconducting lanthanum oxide can be epitaxially grown on a European monoxide epitaxial thin film. This is a ferromagnetic compound. The magnetization is very large. So, even only a 2 nanometer or 6 nanometer European monoxide almost destroy the superconductivity of this lanthanum monoxide because this is a ferromagnetic semiconductor possessing the very strong magnetization. But anyhow, these heteroepitaxial structure can be used for the platform of the superconducting spintronics. So this is a summary of the second part. This is a very stable layers oxide, R2O3 or RO2. This is a almost non-magnetic and completely insulators. But layers monoxide in this study, this is a metastable phase with a divalent layers ion. This is an unusual balance. And some of them are reported previously many years ago, or only gas phases. But all of these compounds can be grown on layers monoxide like this. So this red one is a new solid phase, and these are the superconductor or semiconductor or ferromagnetic semiconductor also, or ferromagnetic metal. So it is very interesting. So in this case, by changing the 4-electron number, the physical properties are not so changed. But in case of the layers monoxide, by changing the 4-electron number, the physical property changes very, very significantly. Some of them are superconducting, some of them are ferromagnet. So this is these are promising electronic magnetic materials. So this is a final slide. So there are various new metastable compounds and new metastable functional materials can be unveiled or discovered by developing the novel chemical approaches. So today, the first one is a superconducting R2O2 bismuth. This superconductivity is discovered by adding oxygen or other elements. And also by using the novel solid phase epitaxy, we can obtain highly conducting antimonadic square compounds. Also, by using the epitaxial thin film growth, we can obtain first single crystalline or first solid phase layers monoxide. This is an interesting compound as magnetic or electronic materials. So thank you very much for your attention.
Sensei, for your insightful and interesting talk today. Unfortunately, we are limited of time, so I'll open for 2 questions for this session. The first one is from Dr. Mirza Saputra. Okay, so is it possible to make a rare earth monoxide using sputtering? What is the specific requirement to make a rare earth monoxide? Please.
Okay, so today we use a pulse laser deposition, but also the sputtering is also the high energy thin film growth method. So I guess sputtering is also possible to make a layers monoxide. But probably ultra high vacuum equipment is necessary?
According to the literature, Indonesia has abundant rare earth element. Is there any real device that use rare earth compound as the main element? For example, like to replace silicon. Hai, dozo.
Yeah, this is a more general question. So, yeah, rare earth is a very important. So, my study is more or less some scientific oriented study, but the rare earth element is often used in the permanent magnet. So, for example, recently many countries try to make electric vehicles. So for electric vehicle, their strong motor is necessary. So for such a strong motor, for example, dysprosium iron boride ferromagnet is the most important candidate for the strong magnet.
I see. Okay. Okay, thank you very much. Maybe one more question, if it's okay. About the superconductor material, you use many kind of elements, right? So I'm wondering how you choose which element actually is best for a superconductor.
Oh. In order to obtain higher superconducting transition temperature, non-magnetic rare earth element is important. For example, the lanthanum or something. But in order to study some interesting physics, such as fermion studies or some competition of the superconductivity and ferromagnetism, magnetic rare earth ion is more interesting.
I see. Okay. Okay, thank you very much, Fukumura Sensei. Okay, I think we'll end this session, but before that, we would love to give a certificate of appreciation to Professor Fukumura.
Thank you very much.
Right. Okay, so I think wait. So thank you very much, Professor Fukumura, for giving a very nice talk for today's conference. So here is the certificate of appreciation.
Thank you very much.
Okay, so thank you again. Hontoni arigatou gozaimashita. I'll give you back the time for the Master of Ceremony. Good afternoon.
ありがとうございました。
Thank you, Professor Tomoteru Fukumura, for the fascinating session, and thank you, Dr. Prastika Krisma Juwanti. Ladies and gentlemen, it's time for the parallel session. For the presenter, please join the Zoom meeting based on the schedule provided. And all the participants, please refer to the booklet for the topic and the link. The parallel session will start at 14:50 GMT+7. Once again, it's time to parallel session. For the presenter, please join the Zoom meeting based on the schedule provided, and all the participants, please refer to the booklet for the topic and the link. Thank you.
senantiasa berjalan. Zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. senantiasa berjalan. Zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era Society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi. Waktu senantiasa berjalan, zaman selalu berubah. Perubahan adalah suatu keniscayaan. Hadirnya pandemi COVID-19 mulai awal tahun 2020 telah mengakselerasi perubahan zaman tersebut. Perubahan tidak hanya terjadi pada sistem kemasyarakatan, melainkan juga penggunaan teknologi yang begitu dahsyat dan memaksa kita untuk beradaptasi dengan sigap. Era revolusi industri 4.0 yang sedang berlangsung, era society 5.0 telah berada di depan mata. Fakultas Teknologi Maju dan Multidisiplin yang dilahirkan saat pandemi COVID-19 telah hadir dan berkontribusi dalam menyiapkan sumber daya manusia yang siap menghadapi perubahan zaman ini. FTMM telah memberikan sumbangsih pemikiran, karya, dan prestasi yang membanggakan di usia mudanya. Berdirinya Pusat Riset Energi Baru dan Terbarukan, karya-karya inovatif unggulan, terbitnya artikel di jurnal internasional bereputasi, dibuatnya robot Arta dan Isana yang membantu penanganan COVID-19, serta pengabdian masyarakat tentang pertanian hidroponik berbasis IoT dan energi surya merupakan bentuk nyata kontribusi FTMM untuk bangsa dan negara ini. Mari adik-adik calon Satria Airlangga bergabung dengan kita. FTMM beraksi dalam kolaborasi.
today. Ladies and gentlemen, welcome back to the main Zoom. The parallel sessions will conclude our event for today.
Thank you for attending the first day of Icatam 2022. We apologize for all the inconvenience today. Do not forget, we still have the second day of Icatam 2022. Tomorrow on October 13, 2022.
The event will start at 8 GMT plus 7.
Thank you and
stay
stay
healthy, and see you tomorrow.
Sorry.